Alright, hello. In this short video we're going to be looking at derivatives of logarithmic functions, and along the way we'll introduce a new method of, or new technique you can use for differentiating called logarithmic differentiation. But first we want to establish there's rules for these functions. So as a reminder, thinking about logarithms and logarithmic functions, what we have in mind is our base here. So if you've got positive a with a not equal to 1, thinking about the log base a, that function, well, that means y equals log base a of x is equivalent to a to the y equals x. Remember, logarithms are inverses of exponential functions. So one way we could think about, we haven't talked about the rules for logarithmic functions yet, but one way we could try to find the derivative is to keep in mind this idea here and use implicit differentiation. So that's what we're saying. That's what we're saying there. So doing so, a little crowded here on the slide, sorry for that. This is what we have right there. So to use implicit differentiation, looking at the right hand side first, derivative of x with respect to x is just 1. Nothing crazy there. Derivative of a to the y, we'll remember the general exponential function, that derivative is itself times natural log of b. So I've got natural log of a times a to the y, and then because we're doing implicit differentiation, we're really using the chain rule for that. We've got that inside function y, and so you tack on that dy dx term. So we want to isolate that on its own, easy to do in one step, divide both sides by natural log of a times a to the y, and then remember a to the y is just x. So we end up with that. And as a nice summary, I've got it right here. So the derivative of log base a of x is 1 over natural log of a times x. That's what we had down here. Yeah. In particular, if you're looking at the natural log of x, which is the logarithm we use most often, or logarithmic function we use most often, that would be when you've got base e, log base e is denoted natural log. Natural log of e is 1, so you just have 1 over x. So the derivative of natural log of x is 1 over x. As kind of a side note, a neat application using the chain rule with this rule is with the following. So the derivative of natural log of a function, I mean, assuming you know where it's defined and all that business, but the derivative of natural log of the function would be 1 over the function times the derivative of the function using the chain rule, because that g function is the inside function, so multiply by the derivative of that. And so that's g prime over g, which is, we don't really go into it too much, we don't look at any real cool applications, but it's what's called the relative rate of change of g. So the rate of change is the derivative, and then it's by dividing by g of x, it's kind of how is it changing relative to its current size. It's kind of a side note there, we won't do anything with it. Just kind of FYI. Alright, so when we're thinking of logarithmic functions and we're talking about logarithms, it's always useful to keep in mind their properties. These are the big ones to remember. So the natural log of the sum is the sum of the natural logs. Sorry, I said that completely incorrectly. The natural log of a product is the sum of the natural logs. Natural log of a quotient is the difference in the natural logs. So it's very much not linear. As I misspoke there for a second. And then we've got x to the power. You can bring that power out in front as a coefficient. You got to be careful here. We talk about these usually, these rules where we've got positive values here. So natural log of 6 would be natural log of 2 plus natural log of 3. We have in mind that we've got some indeterminates here. So these things work where they're defined. So like something like if x was -1 and y was -2, this works because it would just be 2, but then these individually wouldn't make sense. So we're just going to assume that they're all positive. So keeping that in mind, you get something like this guy right here. If you wanted to differentiate that, you can do that. We've got our new logarithm rule, and then for the inside you'd have to use the quotient rule, and along the way you would use the chain rule or to expand all that, but it'd be a fair amount of work. If you keep in mind these rules up here, though, we've got this divided by that, so there's the difference there, and then that 3 comes out in front for that coefficient there. And now we're in business. That's pretty manageable to compute. That derivative is now just going to be natural log rule a couple times with very basic chain rule there. So it's useful to keep those things in mind. Now, keeping that in mind, that's kind of basically the idea behind this new method we're going to talk about called logarithmic differentiation. The idea is you're going to apply, you want to be able to apply logarithm properties. And if the logarithm's there, then you just do it. But if it's not, you can kind of bring it in and then use implicit differentiation and figure out your dy dx. So summarize a little bit nicer here in a couple of steps. Some kind of general steps for this process are you apply the natural logarithm to both sides of an equation y equals f of x, and use logarithm laws to simplify. Now, this is a little bit of an ordeal to get through this process, so there's certain types of situations where you're going to want to use it, and you'll develop a kind of a skill for recognizing that. If f of x is, you see it as the product of a lot of things, or quotient of a number of things, or lots of powers floating around, then it's useful because of those, again, those 3 rules that we're going to use to simplify. So the simplifying is a little bit hand wavy, not well defined, but we have something in mind what we mean, something that's easier to compute. And then differentiate implicitly with respect to x, and then you solve for dy dx. And this step we're getting pretty good at, but you always use a little bit of practice. So for example, if you want to do something like this, you could do it this way. Let's say option 1. Quotient rule. All right, sorry, I had a little technical hiccup there. So when we could go about this, we could have tackled this before. You can start with the quotient rule, and then along the way, you'd be using the chain rule a couple times. So multiple times. Another way, option 2, and it's not that bad, is with the logarithmic differentiation, and that's what we're going to try. So we're going to say, let's let, working from here, we're going to say apply the logarithm to both sides. And that equals, using some properties, natural log of x plus 5 minus natural log of square root of 3x squared plus 1. And that is 2 times natural log of x plus 5 minus 1/2 natural log of 3x squared plus 1. Won't get too worked up about it now, but something we'd want to be careful potentially with here. Something like x equals -6 is perfectly fine here. Perfectly fine here. It'd be problematic there. So when we're going to look at the derivative values, we, where it's defined, we might be a little bit careful. We could kind of cover up some of that by saying this is the absolute value of x plus 5 if we want. We're not going to get too worked up about it, but just something to keep in mind. So natural log of y equals that. And so now differentiate. On this side I get 1 over y times dy dx using implicit differentiation. On this side I get 2 over x plus 5 minus 1/2 times 1 over 3x squared plus 1 times 6x, I'd use the chain rule there. And I could clean that up and just say 2 over x plus 5 minus 3x over 3x squared plus 1. So that's 6x and the 2 there, 6 and the 2. A little bit of a reduction. So dy dx equals y times 2 over x plus 5 minus 3x over 3x squared plus 1. I don't want that y there. I know what y is. It's right here. So it's x plus 5 squared over square root of 3x squared plus 1 times the quantity 2 over x plus 5 minus 3x over 3x squared plus 1. Did we save more time doing it this way? I don't know. Might have been faster to do option 1. We just wanted to show how to do it. And there'll be some where it is faster to use logarithmic differentiation. There'll be some where you have to use logarithmic differentiation. As the last example here, real quick, suppose we want to compute the derivative for these 4 examples. This first one, got a constant, that's just 8, but it's something raised with something, so that's the point. Trying to make some connections here. This one, a little bit tougher rule. We have something varying. Just use the power rule. For this one, we've got exponential rule. And this one's tricky. It's not a power function because it's not a fixed exponent. It's not an exponential function because it's not a fixed base. So for this one, we'd have to use logarithmic differentiation. There's no way around it. It's kind of a weird, crazy function. But to do that, we've got natural log of y equals natural log of x to the x, which is x times natural log of x. And so to differentiate, we've got 1 over y times dy dx equals, product rule there, 1 times natural log of x plus x times the derivative of natural log of x, which is 1 over x. And so dy dx is y times natural log of x plus 1. And be careful with your parentheses. It's not natural log of x plus 1. It's natural log of x, pause, plus 1. And that's the same as x to the x times natural log of x plus 1. So all pretty simply described functions, just what's varying, and here nothing's varying. Here it's the base, here it's the exponent, here it's both. It gets more and more complicated. This last one we had to use logarithmic differentiation for. That's a crazy function. We haven't seen anything like that before, but we have tools to handle things like this now. So that is logarithmic differentiation. Again, we started with the rules for logarithmic functions, and then a focus on the natural logarithm, a natural logarithmic function. And then from there, reminding ourselves of the properties and looking at this new method, logarithmic differentiation.